Hello, this is Scott Lee, and thank you for listening to this presentation. Today's date is March 12th, 2025. In this presentation, I wanted to go over the concept of thermal expansion, specifically for RBE2s and RBE3s, and how to run thermal analysis appropriately whenever you have RBE2s, and RBE3s defined within your FEM. So the main intent of this example is to determine whether or not we should turn on rigid equals Lagrange and apply CTEs for RBEs for static solution 101 thermal analysis. I'm going to be going over two simple studies. The first study will go over an RBE3 plus plate example. The second example will go over an RBE2 with a plate example as well. So why is this concept important? In the field of aerospace, whenever we do modeling, we obviously use finite element models, and in medium density models, we typically model all the fasteners or most of the fasteners as much as we can at the joints, and typically for elements with dissimilar meshes, where we will model them with RBE3s, C bushes, and RBE3s, combination of all those. And then also sometimes people model RBE2s in their FEMs in various ways. And and as you guys may be aware, in aerospace, we use a lot of composites. Composites is prevalent in aerospace, as well as aluminum, and the CTEs between the two are not the same. So whenever you have a design with composites and aluminum interfacing with one another, there is a CTE mismatch. Therefore, under thermal soak loading, there will be a CTE mismatch loads at the joints between the two components of dissimilar materials. So this is actually quite an important topic to discuss, and I'll go on to the example. So in the first example, as I mentioned, it's going to be RB3 plus shell. And what you see here is a simple shell element with an RB3. The independent node is near the corner of this node here, just for illustration purposes. The left-hand side has a CT of CT of the RB3 is equal to 0. The right-hand side has a CT of RB3 equal to 6.6e negative 6, which is the same CT of the plate as well, which is steel. So when I run a thermal soak, basically just a thermal loading, notice the differences in behavior of the RBE3 between the two. Notice how basically notice the differences in the deflection of the RBE3, especially the dependent node. The dependent node on this left-hand side is basically deflecting in a way where it is the average of the four independent nodes, 1, 2, 3, 4. And on the right-hand side, you can see that this dependent node is displacing in a way where it is essentially matching up with how the shell element is displacing, as you can see here. It'll be better for me to illustrate that by actually showing you an animation deflection plot. And as you can see here, let me move this out of the way. It's not the easiest to see, but if you look very, very closely, you'll notice that the right-hand side figure seems to be more accurate and makes more intuitive and physical sense on how the RB3 should be displacing versus the left-hand side. And as I mentioned, um, what you would expect to see, right, of the RBE3 is to expand in a way where it is basically following in conjunction with the shell, right, which is what the right hand side is doing. The left hand side is not doing that. It's simply just displacing as the average, as I mentioned, of the four independent nodes of the shell. And so this one is not right, and this right one is right. So let me kind of go over how this model is set up. It's just simple shells with RBE3s. Uh, I've made the dependent node skew towards one corner just to illustrate the purpose of the differences between the two setups. And as I mentioned, the left hand side has an RB CTE of 0, and then the right hand side has a CTE of the RBE defined as 6.6 e negative 6. And then keep in mind, I'm running a thermal soak, so initial temperature of 70 degrees, my final temperature is 170 degrees. And in order for us to turn rigid equals Lagrange on, which basically takes into account rigid element thermal expansion, it's this button here. And my analysis load case setup is defined here, where I have a final temperature in the load section, and the initial conditions has an initial temperature defined. And then the boundary condition is just fixed at one corner of the shell. So in this example, one can see that, hey, yeah, the right hand side looks a lot more reasonable and makes more sense than the left hand side. And so basically, in conclusion, the way that we need to set up RBEs in our FEMs is defining a CTE within the RBE3. Don't keep it at 0. Whenever you create an RBE3, it's just defaulted to 0. That is not correct. You should actually define the CTE of the RBE3, which is basically the CTE of whatever it's connecting to. So the RBE3 here is connecting to the shells. The shell is made up of steel, so you use the same CTE of the steel of the shell. And then you, like I mentioned before, you do need to turn on rigid equals Lagrange, basically rigid thermal expansion turned on within the analysis set. Another example is in my second example, which is consisting of RBE2s now, not RBE3s with a shell. So in this example, we have a multiple shell elements meshed with a hole in the center with an RBE2. The left-hand side, the CT of the RB2 is equal to 0. The right-hand side, the CT of the RB2 is equal to 6.6 e negative 6. When you run a thermal analysis, notice the difference in displacements between the two. You can notice that the hole on the left-hand side is basically not able to expand outward. It's being restricted by the RB2 from expansion, whereas the right-hand side, the hole is able to expand freely. And then also look at the max principal stress results. Notice that the left-hand side, we're seeing a state of high stresses being developed within the shells, whereas the right-hand side, we are in a zero state of stress, which is correct, which is accurate. In this example, for just a thermal soak, the body should just be displacing in a free way where there is a zero state of stress. And that's what the right hand side is showing. Let me also show the animation plot, deflection animation plot as well. So not you gotta look very closely here, but notice that this hole is being restricted from expansion. That's not what you want. This is not accurate, right? And that's because the CTE, the RBE2 CTE is defined as 0. The RBE2 is essentially acting as a constraint and basically holding the nodes along the hole as a basically rigidly, and it's not free to expand. Whereas you can see these nodes and elements here are free to expand, and therefore it's generating a zero state of stress, right? So in conclusion, basically, the point of this presentation is just to warn and just basically give notice to any FEA analyst out there in the aerospace field or any field that's using FEM. Whenever you are modeling these RBE2s, specifically RBE2s, you need to be very careful whenever you do thermal analysis because the thermal analysis will give you unrealistic results if you do not model the RBE2s correctly. And therefore, this presentation is just to illustrate that yes, you do need to define CTEs within the RBE2s and RBE3s, and you need to turn on rigid equals Lagrange in order to get accurate stress results, accurate joint loads within your FEM, especially when you have RB2s floating around in your FEM, especially if you have aluminum to composite interfaces and you're modeling the fasteners using C bushes and RB3s. So that's the main intent of this presentation. Thank you for listening and have a nice day.